Hi, welcome back. So let's look into linked data. You've been using linked data all the time. When you did your experiments with DBpedia, you used one knowledge base in this linked data project. So let's look a bit more into the principles that went into building this linked data cloud. You've seen in the videos from Tim Berners-Lee that one of the main motivations is to make data available, raw data. Yeah, pretty much any website has a database behind it, but you don't have direct access to the database. You have some kind of web interface, and then you can only interact with that database or data set through that web interface. The linked data project was to basically get rid of this web interface and make the data as it is, the raw data available on the web, so that anybody could look at it and, more interestingly, combine data from different sources, link them together, and build intelligent applications, mashups, semantic networks, and so on, that can make use of this data to get some interesting new insight. So two important principles were: you have to make the data sets available online without any kind of web interface for humans, the raw data, and you want to make links between these data sets. So you don't want to have this silo effect that I talked about a few times. You want to have data connected with other data. And as a nice guideline, there is this 5-star principle for data. So depending on how good your data is, you get between 0 and 5 stars. You get your first star if you make your data available on the web in whatever format. So it has to be an open license, like open source license or Creative Commons license, so that other people can reuse the data, but that's the only requirement. It can be any kind of data format. So that's 1 star. You get a 2nd star if your data is available in a machine-readable structured format. So for example, instead of having an image of a table, you have something that you can read directly into a program, like a spreadsheet. You get a 3rd star if you publish your data in a non-proprietary format. So instead of using something that's application-specific, like Excel, which you need Microsoft program to open it, you use an open standard, like a comma-separated value file. You get 4 stars if you do all of the above, and additionally you use open standards, in particular RDF, RDFS, and so on, to identify information. So at this point, you have these URIs that can be used by others to pinpoint a specific piece of information. And then finally, you get 5-star data if you do all of the above. Yeah, you publish your data in this RDF format, open source, and you also link your data to other people's data. So for example, you link your information in your knowledge base to another knowledge base like DBpedia, so that then people can traverse and further explore the data. So that were the guidelines, and as you've seen in the video, people started both publishing data in this format and also started experimenting with what you can do with the data that is available. One of the very early initiatives was DBpedia, which you've used a couple of times now. And as you've also seen, DBpedia is an automated knowledge base that was derived from Wikipedia. So you all know Wikipedia. Yeah, there is information available about pretty much anything you can think of in multiple languages. And this is all written for humans, but it would be great if an AI, an intelligent system, could also make use of all of this data. So they looked into converting this unstructured natural language documents from DBpedia into a structured format, into a knowledge graph. And the way they did this in the very beginning is with these info boxes that you see in many articles. So DBpedia, at least in the first couple of years, wasn't looking at the text content that you read at all. It was looking at the info boxes you have for almost all major entities. So, for example, for a city, you have information like who's the mayor, what country is it in, how many people are living there, and so on. And this is already in the kind of structured format. So you can simply take the subject of the page, turn this into the subject of the triple. Then you have the various entries here in this info box, like population. You can translate those into properties, and then the values are either literals or they are links to other entries. And in this way, you can create a big multilingual knowledge graph automatically. And this is essentially how DBpedia came to be. There's, of course, additional processing in DBpedia, for example, automatic linking to other open data sets. You've seen some of them, like in the geographic information. And they, in turn, added links back to DBpedia. So basically, from these other data sets, you could go back to DBpedia and get more information about an entity there. Or you can go from DBpedia into another knowledge base, like a GeoNames, and get further information about geographical information. So this is what enabled all these things that we talked about, intelligent systems that can get more information and combine different sources to make new conclusions. So this started out more than 10 years ago with a number of databases. DBpedia was sort of the core because it's sort of domain independent. You have information about pretty much anything in DBpedia, right? You have cities, countries, movies, people, restaurants, pretty much anything you can think of, you can find in DBpedia. So for all the other more specialized databases that are based on music, geographic information, music, images, and so on, they could easily link back to DBpedia. So this is how it looked like in the very beginning. The first data sets came online and using this format started linking to each other. And then it very quickly grew. Even in the first year, more databases came online. 1 year later, there were already quite a few more. And this continued to grow over the first couple of years quite rapidly. Just like in the early days of the web. In the very beginning, there were a few people publishing websites using this HTML thing, and then it quickly exploded from there. For a couple of years now, there is really no nice picture of this anymore because it would be way too big. But you can go, for example, to this lodcloud.net, and there is a automatically generated partial graph, at least, of various databases. Maybe I'll just open this online. So you can see the various data sets here. It's all way too small to actually be able to read it. You can still see in the middle, there is DBpedia, and DBpedia connects with almost everything on the linked open data cloud. The various knowledge bases, there are color coded, so you can see some that are cross-domain, but others are specifically about biological data, linguistic data, social networking data, and so on. And then you can further zoom in, explore, and look at these data sets. And then once you click on the data set, you get further information, like how many triples there are. This has 1.5 million triples, information about license, where it's located, and some of the data sets you can download. Some of the data sets are publicly accessible or have a public Sparkle endpoint. And in that case, you can connect directly and experiment with them. So look around the linked open data cloud so you get a bit of an idea, and you can also search if you're interested in something. You can check if there is a data set on the linked open data cloud that you could use for your application. Okay, so let's look at the underlying principles of this linked data initiative. So this was first proposed by Tim Berners-Lee back in 2006. You can read the original proposal here on the W3 website. Now the question is, what is different to what we have done so far? We learned about RDF, RDFS, we learned about Sparkle. Is there anything different or new for linked data? And well, essentially, no, there isn't. It uses all the technologies that we learned in the last couple of weeks, but there are a few design issues that you have to follow to make your data into linked data. So the first question is, what is a link? And a link is just a triple where you have the subject in one graph and either the predicate and or object in a different graph. So with this, you can have a number of different types of links. For example, you can have a link that refers to an object in a different knowledge graph. You can have, for example, the subject Concordia in one graph, and then the country it's located in a different graph, like Concordia in DBpedia, and then you have a triple where it links to Canada in the Wikidata graph. You can have a relationship link, so where you link objects related to a given one, like from the person to the city they live in. And finally, you can have vocabulary links, and this is also something you've already used. For example, you had a definition of a student, and you said that student is a subclass of fourth person. And then this is a different graph. This is the fourth knowledge graph. It's in a different namespace. It's in the fourth namespace. And your student, we used so far this example namespace, but when you build an application, you have your own application namespace. And that's an example for linking across these two different namespaces using the vocabulary. So these are the three types of links. How can you create them? And again, you have seen how this works on the technical level. If you talk about linking on the instance level, linking IRIs, the one we looked at is OWL same as. So this is one of the most widely used way of connecting IRIs between different graphs. But you have to be a bit careful with OWL same as, because it makes a very strong assumption that these two IRIs are identical. Now, for example, you link Canada with OWL same as from DBpedia to Wikidata. That is probably okay. But you might also have cases where you have two things that are just similar, and then using OWL same as might lead to wrong conclusions, because in terms of the logic, it's assumed to be symmetric and transitive. And if one term is sort of a bit broader than the other, then this is no longer a symmetric relationship. So when you use OWL same as to link to knowledge graphs, you have to be sure that these two are really identical. You've also seen this type of link here, RDFSC also. So again, you can link two graphs with each other, but this is a very weak reference. Now, this just says that these two are related in somehow. Now, there's just a reference. It doesn't tell you what this C also is. Is it a definition? Is it an example? Is it the same entity in a different graph? So unlike OWL same as, which is very strong, this is sort of the complete opposite. It's a very weak link between these two IRIs. And then we have also seen how to use vocabularies to link entities. We've looked at scores, and there were various predicates like exact match, broader match, that you can use to link terms. And similarly in FOVE, there's something like FOVE knows, which has a very specific meaning for creating the link. So that's at the instance level. We link a concrete instance like a person, a city, university. The other type of link is at the schema level. So again, one of them you have used already, for example, using a subclass relationship. And then we linked on the schema level, for example, the student with the property or the class in something like Foth. For this, you can also use vocabularies. Again, we've seen example in SCOs for broad match, narrow match, and so on. And I briefly mentioned OWL as the richer version of making vocabularies, these ontologies. And I briefly mentioned you can have something like equivalent classes, equivalent property, and so on. So when you build an application or you build a knowledge base for linked data, these are the 4 core rules that you have to remember. First, you have to use URIs to name things. Now, that's the principle of an RDF entity, a subject. You give it a URI. The second important point is that the URI is an HTTP URI, so that you can go onto the web and look up the URI. And then when you do this, you get useful information back. Again, using standards like RDF, Sparkle, and so on. And finally, don't publish a silo. Include links to other URIs so that from one entity, you can go to other entities. Let's talk a bit more about how to make your own URIs. So far, we didn't really talk about this because you made something like this example.com URI. And obviously, in a real application, you don't use example.com because, well, this is just for testing purposes. So the first principle we just talked about, you use HTTP URIs, so you can use the web standard, the web protocol, HTTP, and so on to receive information from this web server. When you do this, I also mentioned the second principle that you have to use a domain that you control. Yeah, I gave you the example where I made up a URL using Concordia, where I said http concordia.ca/comp 674/week3/slide4. And it's a legal URI, but I'm not controlling Concordia URL. When you try to retrieve this information, you're not going to get anything back. So when you want to publish data, you can only do this under a domain that you control. You could make a data set with somebody else's domain and still offer this for download, but it would be very bad practice. When you make up the URIs, you should try to use some kind of natural key. This doesn't really have a technical reason. This is just easier for a human to understand, to debug, to query, and so on. Additionally, you should use URIs that are neutral in the sense that there are nothing like implementation details in the URI. Now, for example, don't have something like HTTP, Apache Jenna, Fuseki version 3.5 in the URI, because this is something that's supposed to be out there and published for many, many years. And when you switch your implementation, you go from version 1.4 to 1.5, you don't want to change all of these URIs where you published your data. So you can have a version number related to the semantics, to the vocabulary, but nothing like technical implementation details in there. And the last one is if you want to use fragment identifiers, you have to be somewhat careful. Yeah, remember, you can have something like a hash fragment or a slash fragment. And at this point, I don't really want to go too much into the technical details. Depending on what you want to do, one can be better than the other. If you're really building a linked data set, then please look up the discussion on which one you should prefer in a given context. So to summarize, how do you make linked data? Something that will do in the project as well. You'll make a knowledge base where you have to follow linked data principles. First, you have to make your data 5-star, open license, structured format in RDF, and creating links to other data. You have to give it a URI that follows the guidelines that I just showed you. You have to select an appropriate vocabularies. We talked about this a few weeks ago. You make data self-describing, understandable to others. If an existing vocabulary doesn't have everything you need, you can extend it by, for example, inheriting from a class or extending it in one of the other ways. And then finally, you have to link your data to other knowledge graphs. For example, you can link information to DBpedia, or if it's something domain specific, to one of the other graphs that you've seen in the linked open data cloud. Now some biological, biomedical, geographical, or whatever information you have. And then finally, you publish your knowledge graph on the web. We talked about this last week. You can publish, in the simplest case, just a dump of the data, now the raw data set in any format like n-triples. This would be published, but even nicer, it's even nicer if you can publish it using something like a Sparkle endpoint so others can query it directly. Okay, so much for linked data, linked open data. And in the next lecture part, we'll talk about some more principles and techniques for building a knowledge base. See you then.